Welcome back, everybody. We're going to go ahead and give this a go from our home station. You'll probably notice that the background is a little bit different. We've got this nice wood with a scratch that came from me actually setting up all this stuff. Did not realize that was going to be there. Whatever, though. We're going to be working through our examples involving power now. Now, I'm going to do both of these in one go because the first one's kind of straightforward. The second one's a little more complicated. There's going to be some explanation that's going to need to go on here. This is at my house, so hopefully we do not hear any of my cats in the background. If you hear them screaming, I promise we fed them. They just don't believe me whenever I say that. Now, our first example that we're going to be working with is the one involving the jogger. Now, it says a 60-kilogram jogger runs up a flight of stairs in 4 seconds, which, depending on the flight of stairs, I guess is either really impressive or really slow. So we've got our flight of stairs right here. And we've got our guy who's just, running super fast up the stairs. It's his little, hands like running back and forth. As you know, I'm terrible at drawing. But he's running up the flight of stairs in a time of... We've got a time of 4.0 seconds. And he weighs 60 kilograms. The height of the stairs is 4.5 meters. So a pretty short flight of stairs. 4 seconds actually makes a lot of sense. And then it says, what is the jogger's power in both watts and in horsepower? Watts being the SI unit for work. It's just joules over second. And then horsepower is commonly what we use in the United States for things like cars and stuff like that. As I think I mentioned in the notes, I'm not actually sure if that's an international unit, so please let me know that. Now, first thing that we need to think of is the work that's going to be involved in this. Obviously, this whole chapter is involving work. In this case, the only thing the jogger is really fighting is going to be gravity. Gravity is our focus. We are concerned with how much he's going to have to go against gravity. It doesn't really say anything about his horizontal speed or going to the side or acceleration to the side or anything like that. We're only really concerned with the vertical thing. So just like our backpack one, we're only really going to be worried about that. And if that's the case, then our work is equal to our force fighting gravity is equal to mgh. Or, as I believe I've been using, mgdy. It's going to be mass, gravity, and the distance that we actually travel upwards in this case. So we can actually, we have all of that information. The mass is 60 kilograms. Our gravity, in this case, it is on planet Earth. You should always assume it's on planet Earth, so it's 9.8. And then our distance in the y direction that is going up is 4.50 meters. And then this, if we want to turn this into our work equation, or power equation, power just equals work divided by time. So we can just take all of this information, our 60 kilograms, our 9.8 meters per second squared, and our 4.50 meters, and we just put that over the amount of time it took him to run up the stairs. So that's 4.0 seconds. And if you do that, you get... rounded to sig figs, I believe, and it's 2 sig figs. I think it should have been 60 point, so we're going to take this to 2 sig figs. So you will get 660 watts. Okay, so that gives us an idea of power, but we don't really have a good reference for that. We also don't really have a super good reference to horsepower unless you are good with cars, but let's convert it into horsepower anyway. Maybe that'll make it a little bit more understanding. So this is kind of part A. I didn't actually separate them into part A, B, and C, but this is kind of part A. For part B, we're going to take our 660 watts and we're going to set it up as a dimensional analysis. And in our example, it says that 1 horsepower is equal to approximately 746 watts. So 746 watts is going to go on bottom. 660 divided by 746 gives you 0.8847, which we are rounding to 2 sig figs. So you get 0.88 HP, or horsepower. Okay. That is, I guess, basically you could say 88% of the power a horse has if we're basing horsepower on actually horses. But I believe that's kind of the original intention, but I don't know if it's actually perfect to that in this day at least. Now, for energy, well, remember that energy and work, in this case, are probably going to be the same thing. The energy that he's using is entirely focused on getting him, at least in the Y direction, to go up the stairs. There is going to be some horizontal energy that's being exerted here, but the work, the actual distance that he's traveling, and the stuff that we focus on the problem, and more importantly, the stuff we actually have information to solve for, is going to be just vertical. And so the work in the vertical direction is what we did right up here. This thing right up here at the top, where we took our 60 kilograms, our 9.8, and our 4.5. So there's a reason I didn't solve for that earlier, is because, well, that's actually the answer that you would have gotten here. I assume since some of you guys like to plug in all the numbers and like do it like this and then take that number and put it on top, you might actually already have this number. But we're just going to go ahead and do our 60, our 9.8, and our 4.5. Multiply those three together, and you will get your work, which is 2646 joules. Or to sig figs, if we convert it, we get 2,600 joules of energy needed to go up there. Now, I do want to add one extra question that's not mentioned on there. So you may want to take a moment to think about this before you unpause and like actually hear the answer to it. My question is that actually how much energy this person needed to go up the flight of stairs? We're ignoring horizontal direction, but is this the only amount of energy they need to vertically climb the stairs? So, like I said, if you want to pause for a moment, think about it. Awkward silence is over. Okay, this is your chance to pause if you wanted to. The answer would be no. This would not actually be how much energy they need. Your muscles don't work perfectly. Some of the energy would have been lost in heat. Even if it's a small amount, there is still air resistance. There's friction on the stairs. All sorts of random places that energy could have been lost. But, you know, in the world of physics problems where we assume everything's perfect, that's a good enough number. So we'll stick with that one. Okay, our next example has a little bit more going on. I'm just going to make sure I pull up the actual problem before I start discussing it. So I know from what I remember about this problem is that we've got a car. So I guess, get ready to make fun of me for my car drawings. And our first thing that we're asked about the car is that car is going to be placed on an incline, or is going to be driving up an incline. So we've got our car. It's a Pinewood Derby car. That's why it looks, so basic. And it tells us the mass of that car is 1,400 kilograms. Okay, that's pretty straightforward. This incline has a theta, or an angle, of 10 degrees. Almost sort of Celsius there, because I'm so used to it from chemistry. And its speed, its velocity, is going to be equal to 22 meters per second. Okay, and then it just asks, what is the power if it also has a frictional force? So friction is pulling it backwards at a certain amount of power. Now, I drew this as just a basic sketch. I don't know if I'm going to have enough space in here to clearly lay it out, but we'll try it. So we've got FFR, so that's our force of friction. That's this arrow right here. So friction's pulling backwards. And then we've got our actually force of, I'm going to use FD for force of driving. It's the actual driving of the car. Now, what else do we have? Well, it's in contact with the surface, so perpendicular to that surface is the normal force. We probably won't need that because, again, cars do not, when they drive, they don't, ramp up and, go sideways and go flying and stuff like that. So we're probably not going to need normal force, but gravity is going to point straight down which means it will actually have two components that we can split it into. If we want them to be, instead of it being sideways, if we want to think of it as this direction as our up or our y, and this direction as our x, instead of the little slanted version that we've got right now. Now, the other thing that's important about this question, and the key to being able to do this question, is the fact that it says the car is driving up the incline of 10 degrees at a steady 22 meters per second. That means it has a constant speed, and a constant speed means that acceleration is 0. There is no acceleration. And if acceleration is 0, we know that the sum of the forces is equal to the mass times acceleration, so that means the sum of the forces is 0. That means the thing that's letting it go constant speed is this driving force canceling out the friction and canceling out this little tiny component of gravity that we've got right there as well. So we know that in this case, we take our sum of our forces. They have to equal 0. Our force of driving minus the force of friction, and then minus force of gravity. And again, we're going to treat this as the x direction, because if we turn it this way, it would be horizontal, even though it's kind of at an angle. So the force of gravity in the x direction. So this minus this minus this. The driving minus the friction minus the gravity should all cancel out. Now we can move both of these to the other side. And we can just therefore figure out that our force coming from the driving, the actual force the car is exerting, is equal to friction plus gravity in the x direction. Okay, now that gives us a really good place to start. It's a little complex to actually get to that point, but that at least gives us a place that we can begin doing the problem at. So I'm going to go ahead and and we've got our F of our driving. We know our friction, because it just straight up tells us that there's 700 newtons of frictional force. And then we just need to say, well, we want this piece of the angle. So if I think of this arrow downwards is gravity. So gravity is just mg. It's just mass times gravity. And we want to know this piece right here. We want to know this. Let me actually reach over and... we want to know these lines that I colored in purple for a little bit more clarity's sake. So we want to know those lines. And we know, based on our angle trigonometry stuff that we've worked on, that theta on the angle, on this piece over here, this 10 degrees, is also the degrees in this piece right here. And if we know that, because of our trigonometry, we can use our trig identities. So this is mg. And then this angle here, if we use cosine, it would be adjacent hypotenuse, because here's our 90-degree angles right there. So this would be our hypotenuse. This would be our adjacent. This would be our opposite. So we're going to want to use sine theta and then times mg. So that'll give us this component that's over here, sine theta mg. Or usually we'll kind of write it the other way around. And I think I'll actually write it the other way around right now just to make it a little more neat whenever you're looking at it. And it makes it so when you plug in your calculator, it works out a little bit easier. So we've got 1,400 as our mass, 1,400 kilograms. I apologize if the camera's shaking. I just realized that me moving my hands on the desk might be shaking it. If that is a problem, please let me know. I'm currently trying to figure out exactly how I want this camera to be situated and not be doing a bouncing thing. That sounds very obnoxious for you guys. And then sine theta would be sine 10 right there. Okay, and we know that these are going to tell us whatever our driving force is. So if we add these together, plug these into our calculator, you get 3,082.45, something like that, newtons. Okay, now that we know our force, or we know our, in this case, because it's the only force going in that direction, we want to know the work that the car, or the power that the car is exerting. So this is the work that the car is actually putting in. This is gravity doing this work. This is friction doing this work. If we want to know the power a car is exerting, we wouldn't say, well, the friction of the tires is exerting a power. That's not the car. Your engine doesn't make your tires stick to the pavement, and your engine doesn't pull down because of the, well, your engine does get pulled down by gravity, but it's not like the engine running like is what pulls the car down. If you turn off your car, it doesn't float away. So the movement forward is the only thing that's actually being powered. If we use our P, it's the only thing being powered from the car. So power in this case is going to equal to our work, which the only work the car itself is doing is driving. The car, again, you don't pull a lever to activate friction or anything like that. And then we're going to divide that by time. Okay. Now, if we just only had this equation, this would not really be helping us out because we don't actually know a time. However, in the notes, there was a rearrangement that we could do. And the fact that maybe there is actually... we could do some other stuff to solve for this time and try to get this piece. But instead, if we know the force that it's exerting and we know the speed that's exerting, we can just plug that in. We can use that as our equation. And you'll have power equals work over time and equals force times velocity. This will be the equation that you'll be given. So let's just plug in our force, our 3,082. And then we'll multiply that by our speed. Now back here, it told us our speed was 22 meters per second. So we're going to multiply that by 22. Multiply those guys together. You get 67813 watts, which is about 91 horsepower, which, again, I don't actually know cars. That might be a lot. That might be a little. I don't actually know if that can tell you what type of car it is. But we do want sig figs. And in this case, 22, we aren't going to use that 10 degrees. We'll use that 22. So we'll go ahead and say it is 68,000 watts. Or remember, if you use your metric prefixes, you could actually also instead say that it is 68 kilowatts. But I wouldn't expect you to have to do that. You aren't required to do that every single time. Okay, so that was for part A. Part B is actually even easier. So let's go ahead and use part B. And part B says the same car, so we know that our mass is still going to be 1,400 kilograms because it's the same car. I mean, I guess someone could have like dropped off or something like that, but as far as we know, same car just means it's got the exact same mass. And then it wants to know, well, now you're accelerating. You're going from a initial speed of 25 meters per second to a final speed of 30.6 meters per second in a time of 5 seconds. And it also says that there's the same frictional force. So our F of friction is still going to be 700 newtons. Oh, I apologize for that. Man, I feel like it's going to get so infuriating when you can see, but you like are yelling at your computer for me to move up, and I'm not going to do that. Man, yeah, that's going to be super annoying for you guys. Okay, first thing we need to do, though, we need to figure out our acceleration. And you might be thinking, okay, well, we'll use like F equals ma, or we'll do something like that. But again, think back and try to keep in mind some of the older equations that you do, or that we've done. It will save you a lot of time. In this case, acceleration is just the change in velocity over time, and we know two velocities and we know a time. So we can do 30.6 minus 25, and then over our time, which is 5 seconds. And if you do that, you'll get your acceleration is 1.12 meters per second squared. Now, all we have to do is first, well, we are going to plug into F equals ma, but we found a this way. If you would have just started with F equals ma, you probably would have had a pretty rough time. So F equals ma, and it is accelerating in this case, so there is an acceleration that's going to get plugged here. This guy is going to get plugged in right there. And then what forces do we have at play? Well, it's on flat ground and it's not flying, so gravity and normal force are not really affecting it because, you know, if we draw our little my crappy car here. We'll have the normal force working upwards. We'll have gravity pulling downwards, but the car is accelerating forwards, and it's got friction pulling it back from behind. So we can kind of ignore these guys. They're not actually doing anything in this problem. If we needed to calculate friction, we would use the normal force, but we're already given the force of friction. So we've got the force of, I'm going to still use D for force of driving, minus the force of friction. Whatever the car is experiencing is coming from the force the car is exerting, and then minus the friction that's coming off. That's the only place this force could be coming from. That's the only reason we could have this acceleration that's going on here. So if we rearrange this, we can get our force of driving is equal to the mass times acceleration plus our force of friction. So we're going to take our mass of 1,400, multiply that by our 1.12, and then we're going to add our 700 to that. And that gives us 2268 newtons. I think I rounded a little bit there, 2268. And then finally, we don't want newtons, we don't want a force, we want a power. So for power, we need to go and say, well, we don't have, if we look back here, we have a time, but we don't really have the full work necessarily that's going on. You could argue that, you know, the work that's happening here is going to be some other stuff that we could calculate, but instead we can just use the fact that, well, we know the force and we know the velocity. We know the speed they're going at the end is this speed right here, this 30.6, and we know the force because it's what we calculated up here. So let's go ahead and do our 2268 newtons, and then we'll multiply that by our final velocity, 30.6 meters per second squared. And that will give us 69400.8, which is approximately 93 horsepower, or again, to round to correct sig figs, you just get 69,000 or 69 kilowatts. And again, 2 sig figs because 5.0 seconds is our smallest number of sig figs in the problem. All right, I hope that helps you guys work out some of these power examples. I know these were a lot easier. This one is really intimidating up here because it involves the whole angles situation where you've got like a theta and it's going up a slope. But really all that just means is you just have to add trig at this part exactly right here, just to do account for gravity pulling backwards on the car. I still definitely think that dropping the ball on the spring is like the hardest type of problem that you'll really need to be worrying about for this chapter. I hope that helps you guys. If you have any questions, as always, you can put them in the box to the side. You can email me. Other than that, though, have a great rest of your day, and hope to see/hear from you soon.